Good morning, everybody. It's such a pleasure to have Professor Peter Jan van Leeuwen here from Colorado State. So Peter has been in Colorado State since 2018. He's a towering figure in the realm of data assimilation. He's going to talk about it more. So he has been a professor in the Department of Atmospheric Science in University of Reading since 2009. He has served as a director of Data Assimilation Research Office for many years. And this is a big institution, and it contains like collaboration between 12 universities. He has been the head of the department of the University of Reading, a very large atmospheric science department, a large department with more than 60 faculties, 100 postdocs, and more than 150 PhD students. So I had the chance to just meet Peter in the past AGU meeting, and it was such a pleasure. So he accepted my invitation. And about his background, he received his bachelor degree in physics and mathematics in 1984, Netherlands, master degree in theoretical physics, 1987, and PhD in fluid mechanics from Delft University in 1992. So join me to congratulate and thank him for accepting our invitation. So the floor is yours.
Okay, thank you.
Just happy to have you.
And applause, and you haven't even heard me, right? I'm honored. No, thank you very much for the invitation, of course, and thank you for accepting me, and I thank you for coming. I'm very keen to be here and well, explain some of the stuff we've been working on, and to try to set up some collaboration with the introducers. So I want to talk about nonlinear Bayesian inference for high-dimensional system, and I'm not sure if everybody knows what that is, so I go to that, to every part of that. Before I do that, I'd like to acknowledge my collaborators specifically for this kind of work. That's Manuel Pulido and my present student, Churchy Hu, working at Colorado State, but also still on evaluation. I'm still working at the University of Reading in the UK, and the main funding comes from Europe, actually, still. So the motivation is the following, right? I want to understand systems like this better. So you recognize the ocean here, Africa, South Africa. This is a model simulation. It's not the real world, but it's getting close. A model simulation. The colors are the size of the velocity, so the magnitude of the velocity. The scale is about, well, goes to about 1.6 meters per second. We're talking ocean. That's typical order of magnitude of velocities. And you see, there's there are all kinds of eddies being formed and then destroyed again, and new eddies being formed here, highly turbulent region. And this is actually a very important part of the climate system. Indian Ocean here, Atlantic Ocean here. There's a transport of relatively warm and salt water from the Indian Ocean into the Atlantic, and that water finds its way all the way to the North Atlantic, where it sinks, and we have the whole overturning of the ocean circulation is connected to what happens here. I don't want to overstress it, but it's just one of the important parts of the whole thing. So we want to understand what's going on here, and of course I can study this model, and it means I learn a lot about model world, which is nice, but we want to know something about the real world, so we want to combine this information with observations. And the science of combining results, prior knowledge from big numerical models with observations, typically in the geosciences we call that data simulation. Ocean atmosphere mainly. Oh, it's nice, but okay. So the way we think about it is in terms of the model. We know the model is not perfect. There are uncertainties connected to the model state that we have. So we want to describe those uncertainties, and the same for observations. And the way we do that is in terms of probability density functions. So PDF. I'm slightly lazy. I'm going to use PDF, and it just means probability density function, right? And so at some point we have this probability density function, and one thing we have to do is to propagate that PDF forward in time. I think about when you want to do weather forecasting. We have our estimate of the atmospheric state, and its uncertainty now. I want to propagate that. We want to do a weather forecast for tomorrow. Then we have to propagate this whole PDF forward in time to tomorrow, right? And we have to come up with a way to do that. And as soon as we've done that, then we have to forecast, and then we have the forecast for that day. We wait until we get observations. So now we are tomorrow, and we have observations of what the atmosphere is doing. So these red dots are these observations. And then we have to combine these two sources of knowledge, right? Our forecast with these observations. And then that's what we do. That's what we call data simulation. So for the more statistically oriented among you, that's Bayesian inference. Bayesian inference in the geosciences. And the basic idea is that we have our model with its uncertainty. This is a PDF. The observations with their uncertainty, and the only thing we have to do is to combine these two sources of information. And it turns out that Bayes figured this out ages ago, how to do this. If X is my model state, so there's some notation now, X is the state of my model, so it could be atmospheric state. And Y are the observations of that state. So this is this PDF is my starting point, my forecast, and this PDF over here, Y given X, that's the PDF of the observations. And Bayes' theorem tells us that the way to get to combine these two pieces of information, just multiply the two PDFs. And then we get the so-called posterior PDF, which is the probability density of the state, given these observations. So we have assimilated, we have incorporated those observations. And the denominator here is just a normalization factor, which we don't have to worry about in the kind of method we're talking about. So we only have to multiply two PDFs, right? So what's the big deal? Oh, sorry about the noise. The solution is a probability density function, right? So we're not just looking for a best forecast, right? We want to know the uncertainty in the forecast. It's crucial for all kinds of operations, think about oil or whatever. We want to know how good the forecast is. And you see, slightly provocative perhaps, there's no such thing, at least in my mind, as Bayesian inversion. There is no inversion, we just multiply. That's it. Of course, if you're interested in, let's say, the mode, so the maximum of this probability density, so the most likely state given the observation, then it's useful to formulate this as an inverse problem. But the principal problem is just a multiplication. Now, we hear people talk about big data and this age of machine learning, etc. So how big is it? How big is our problem really? And it's quite interesting. So we're talking about probability density functions, and we want to do this general. We don't want to describe what that probability density is. Typically, we assume things are Gaussian, but in the real world, things are not Gaussian. So suppose we use 10 frequency bins for each variable. So we have a high-dimensional system. And for each variable, let's say the temperature here on the top of this building, the temperature, and I'm using 10 frequency bins to describe that temperature. So a histogram of, 11 bars in your histogram that describes the PDF, the local PDF of the temperature. But of course, I have more variables in my system. I have a big atmospheric model. So let's do a small model with only 1 million variables. Now, we never use that for numerical weather prediction. It would be useless, right? So nowadays, we run models with about 100 billion variables. So this is still a small model, but just let's go. So how many numbers do we need to store? To store this PDF of the atmosphere. With a model with 1 million variables, then we need 10 to the power, we need to store 10 to the power 1 million variables. That sounds a lot, right? But we have these big computers, right? And should be able to do that. Now, just to put it in perspective, you can estimate the total number of atoms in the universe. And this is 10 to the power 80. Okay, we can be a factor 1 million wrong. I don't care, right? It's really not of the same order of magnitude. So just to the data simulation problem is larger than the universe. This is bigger than big data. This is just to big data, if you like. So the whole field of data simulation or of Bayesian inference in this kind of system is about finding the best approximations. And clearly that depends on your application, what you want to do. Now one way we sorry about the noise again, I should have turned it off. So we have these big PDFs, we know we cannot even store them, let alone propagate them forward in time. So what we do, to have a general description of this PDF, we just take samples from them. So this is my continuous PDF, the contours are the continuous PDF, and the red dots, these are my samples. So these are atmospheric states, different atmospheric states. And so mathematically, I say that I represent my probability density just as a sum of delta functions. And of course, I can calculate the mean. That would just be the mean of those samples. I can calculate covariances, etc. This is an efficient, well, maybe not efficient, but this is a very general representation. We want to keep it completely general. So that's my representation. And then I have these, sorry, I think this is the last one. So and then of course we have to propagate. I said one of the problems is to propagate these PDFs forward in time. To do the forecast. And the way we do it, we just propagate each of these samples forward in time. That would just be an atmospheric state that I propagate with my full atmospheric model, right? So nothing special there. And then at any time, in principle, I have, well, this description of my probability density. So that's for my model. And like I said, each of these things is just my full nonlinear atmospheric model or hydraulic model or whatever model you're thinking about, space weather, or you name it. Okay, so now we're going to do data simulation. And there are several ways, and I want to zoom in today on the method that we've been playing with recently, which I think is quite interesting, otherwise I wouldn't talk about it. So suppose, so now we are at observation time. And we want to incorporate the observations. So I have my prior PDF here, my prior probability density, represented by these blue samples. And I can calculate, because I know what the observations are, and I know the errors in the observation, so I know the likelihood. So I can just calculate, in principle, what my posterior is. It's just that I have a nice analytical expression for it, but no, it's actually not analytical, because, sorry, I shouldn't say that, because I don't know what my prior really looks like. I only have this representation. But I can we come back to that later, I can construct this posterior PDF. And the only thing I need to do is to then generate samples from this posterior PDF. Because this posterior PDF will be something weird. It's not a Gaussian or a gamma or whatever, something nice. It does a shape that is not analytic, and we have to come up with a description of it. And the way we're going to do it is we're going to take these samples and we're going to transform these samples from the prior to samples from the posterior. So what we're going to do is we're going to move these samples in state space from prior to posterior. And again, remember, this is all happening at observation time. So we define a flow of these particles, of these model states, in state space, but it's a flow in pseudo time. It's not real time. Because again, in the real time, we're happening at one observation time. That's time. But of course, we can always define this. And so we have to define this flow. And an example here is, this is an example of that flow. So x is again my state. This is the infinitesimal change of that state due to the flow, which I call f here. And there's also a random component. We can add a random component. Later on, we'll kick it out again. But for the general framework, we can have a random component. And again, so S here is the pseudo time. It's not real time. And the idea is that each of these prior particles, I'm going to move them with this flow field such that they go from prior to posterior. Yeah, of course, if you have any questions, then you should ask, right? But if there are no questions, I assume it's all clear. Let's not go there. Okay, so the question is, of course, how do I find this flow field, and how do I define the statistics of that stochastic term there? And Yeah, so if you look at the level of the particles, of the level of these model states, I have no idea, right? It can be anything. I only know something at the level of the probability densities. Right? So, of course, with such a differential equation corresponds a Fokker-Planck equation, which describes the evolution of the probability density. Again, this is in pseudo-time. But as soon as I can have this equation, I can immediately write down the corresponding Fokker-Planck equation. So how the probability density of x changes over pseudo-time. Yeah, I mean, just a mathematical fact. If things are smooth enough, but we assume they are. So at the level of probability densities, I know something. Right? I know that my starting point, so when s is 0, then all my particles are in the prior. And at the end point, which can be s going to infinity or s going to 1, we're going to talk about that, then I know I have to end up in the posterior. Right? So I know the starting point, I know the end point, and I just have to find the flow field and the stochastic forcing there that will bring me from one to the other. And again, all happening in pseudo-time. So we can say something more about the flow field. Of course, it should, ideally, at every step of this differential equation, it should reduce the distance between this intermediate density, P of s. S is the pseudo-time index. Again, starting at 0 and then moving to either infinity or 1. I have to reduce the distance between this intermediate density and the posterior. So I'm starting at the prior, I'm going to move stuff, and of course with every move I want to get closer to the posterior. And so that suggests we need to define a distance. So, but before we do that, let me see. Yeah, I can do this. So let's look at a solution of this form. And we say this intermediate density, I write it as the likelihood times the prior, but then you see that I raise the likelihood with a power s, to the power s. And of course, when s is 0, then my intermediate density is indeed the prior. That's what I want. And when s is equal to 1, I see I have the full Bayes theorem here, so then P of s, this intermediate density, becomes my posterior. Right, so this would be a possible evolution of this intermediate density. And with this expression, I should be able to find what this f is, what this flow field is, and what the statistics of the random forcing is. And actually what you can do, you can take this expression, plug it into the Fokker-Planck equation, and then it turns out that you get this equation over here. So we have the grain of the posterior, and we have the f here, and f is this f is the same as that. Notation is not entirely consistent. Apologies for that. And the same f over here, and this q here is the error covariance of the random forcing, and we assume that the mean of the random forcing is 0. And so we have an expression for q and for f. And as soon as f and q fulfill this equation, then then I have a solution. And but there are infinite number of solutions. Well, actually I didn't count, but I think there are an infinite number. So which one to choose is a question. And it turns out that Fred Daum and his colleagues, they found an analytical solution for this. So there is an analytical solution. And it looks like this. And I think that's beautiful. Actually, the proof for this because it gets quite hairy, is actually, so the way they came up with this was that they did a linear problem. So for the Kalman filter, if you would do the Kalman filter in this particle flow framework, then you find certain expressions, then it's easy to find expressions for f and q. And then they said, okay, let's generalize that. And when they just generalize it, so thinking about what these things mean, then they came up with this equation, these two equations, and they took these and put them back into the equation on the previous page and see if that's a solution. And that is actually quite hairy. It's actually becomes quite complicated, and they needed Mathematica to do it. So the full proof is actually half in Mathematica and half in the postdocs that did the trick. So there's no 100% proof that this is actually the correct solution, but I think it makes sense in many ways. So that's great. So again, we are done, or not. So we have an analytical solution to move the particles from the prior to the posterior, right? So we've sort of solved the problem, you would say. But actually there's an issue. And it is that this P of S, we don't have it as a continuous probability density. We only have it as this sum of delta functions, the delta function representation. Because we only have the particles that move around. We don't have the full PDF. So how do I take the logarithm of a delta function and then take the gradient of that thing and I don't know, right? It's not well defined. So it's not a practical solution, but it's nice that it's there. So we have to do something else. And in 2016, the paper came out where people introduced this for a steady state problem, and the only thing we did was to make it into a sequential problem, so you could use it for weather forecasting. So going back 2 slides earlier, I said we need to reduce at every time step the distance between my intermediate density and this posterior. So first of all, you have to define a distance between probability densities. And you can do many things. We use here the Kullback-Leibniz divergence. You can do Hellinger, total variance, x squared, Weierstrass. You can do whatever you like. This turns out to be easiest. I'm aware that this is not a proper distance because it's not symmetric in the 2 arguments, but it does it for us in the sense that if my PS becomes equal to the posterior, right, then the logarithm, then this will be 1, logarithm of 1 is 0, so then the Kullback-Leibniz is indeed 0, and for any other intermediate density, this is non-zero, right? So for us, it'll do as a distant measure. It will be good enough. So we have to minimize this at every time step. Okay, let's take the time derivative, the pseudo-time derivative of this distance. We can just write it down. It's elementary mathematics. You don't have to. I check the details for you, so you don't have to do that. And then, of course, as soon as I see this term here, I can use my Fokker-Planck equation, plug it in, and then I get the expression like this. Nothing special yet. And then, so there's an enormous rich framework that we haven't explored yet, and we're going to. But at the moment, the first step that we did was to ignore the Q term. So we say, okay, we don't do the stochastic part of the particle flow. We only do it deterministically. That's not necessarily a restriction. You can do anything. In principle, you can do anything you like. Okay. So we assume that this Q, this covariance of the random forcing is 0, and then we get this expression by playing a bit with it. We get this expression for the change of the distance between these 2 densities. Now, the thing is that we still cannot really use it because we still have the PS here, and then the logarithm and the gradient. So we still cannot use this. So we're going to use a trick from machine learning, if you like, and we're going to embed F in a reproducing kernel Hilbert space. Now, if you have never seen it, you think, what's this about? Well, it's very simple, right? Because we just define a kernel, and it turns out we'll have total freedom there. The kernel has 2 arguments. It could, for instance, be a Gaussian. Gaussian with 2. Yeah, that's what we do actually. Yeah, our kernel will be a Gaussian. And this just tells me if I take the inner product of my function f, of my flow field f, with that kernel, then I get f back. So that's the reproducing property. And you see, I put f in and I get f out. And so you see this is well, effectively a convolution. Anyway, so this is all we need. And this turns out to be crucial. Because if I take this description of f, I plug it into that expression for the change of the distance between the 2 probability densities, then I play around a bit, and then I get this form. The thing is, I can interchange the integration and the inner product because they work on different variables. So I can write in this form, and then if I think that okay, my change of distance with time, how does that evolve in time? Well, my flow field is F. So this has to be this part here, the first part of the inner product, has to be the gradient of that Kubrick-Leibniz distance. Because of course the change in KL is the flow field, the inner product of the flow field and the gradient of KL. If you think about it in the geometry, you see it immediately. I think. Anyway, so what we have done, okay, so this line comes from what we had above, and this line comes from the interpretation of what actually happens there. And that means that we can now identify the gradient of this of KL with that integral. So that's good. Oh, and there's one other thing. So we have an expression for the gradient of KL, which is not what we want. We want to find an expression for F. And now we say, okay, but we want this to be negative. We want that distance to decrease. So how can I ensure that? I can ensure that by saying that F has to be proportional to minus that gradient. As soon as I do that, then I get here the inner product of the gradient times the gradient, that will be a positive number. And I do minus that gradient for F, so I get something negative by construction. So even if that all went a bit too fast, the point is that we managed to find an expression for this flow field in terms of the gradient of the KL divergence. And for the KL divergence, we have found that expression, that integral over there. And then we can do some further math. I mean, the details, again, they don't matter too much. Oh, well, actually, they do. And the whole reason of introducing the kernel is actually this step. And we can rewrite this form into this form. And the important thing is, I mean, there's a lot of terms here, right? But the important thing is that PS now appears here as just one PS. PS, the integral of PS over something that does not contain PS. And that's what we want. And why do we want that? Well, we know PS in terms of a sum of delta functions. I know how to integrate over a delta function, right? That's how we do it. So I know PS as a sum of delta functions. So suppose I have n particles, so n delta function, then this integral just becomes a sum over the position where the delta function is infinitely large. So I get an expression for F. So I guess even if you didn't follow all the details, the point is that by playing this reproducing kernel Hilbert space trick, we do find an expression for F that is actually completely general. The only thing we did is that embedding in this Hilbert space, but these reproducing kernel Hilbert spaces are very, very general. And the only thing I'm doing is I'm restricting the flow from prior to posterior to be in that space. And so the assumption is there is a flow in that space that does it. And
how are you guaranteeing that as you're moving along there that it's still physically possible? Isn't it possible to go through a state space that in fact is from a physics, chemistry, or whatever your state variables are, it's just impossible?
Exactly. And that's where the kernels become important, because as you see, the kernels are important. But the thing is, of course, that we do have the so the physics is sort of hidden in the posterior PDF, because the posterior PDF does have the prior, and the prior has the physical relation between all the variables. And so this term is most important to keep us on the right track. But these kernels are also important. Yeah, there's a lot to say there, but actually we still exploring this. This is a very good point. So what we have an iterative scheme. So this is the original equation. So the change of for every particle, so every atmospheric state, say, or hydrological state, whatever, with pseudo time is this flow field. I have an expression of the flow field. I just can write it as discretize that equation, or another way of looking at it, I can see this as a minimization problem where I just minimize the KL divergence. yeah, so it suddenly became an optimization problem, right? These things are the same. Of course, you can see an iterative solution that moves to something as a minimization or a maximization problem. And we run this in practice until this gradient becomes smaller than something. So if you're familiar to, well, whatever minimization problem, you always have that kind of criteria there. Okay, so a few remarks. Yeah, so the strong point of this whole formulation is that we do not need a continuous representation of this intermediate density. We just need the particles and just need those states. And if we look at the final expression for the flow field, we see two terms there. So this term here has to do with the logarithm of the posterior and then the gradient of that. Now that's a term that will push the particles towards, up, there's a minus sign here. So we'll push the particles uphill to the maximum of the posterior, to the mode of the posterior. And so if I would only have this term, then all the particles would just converge to the mode. And we would have found a very expensive minimizer, right? Although, well, there's something to say for it. But you also see there's a summation here, right? So we calculate that gradient for every particle, and we take an average gradient. And each of these gradients is weighted with the kernel. So you see that these particles are talking to each other while doing their gradient descent, or their, well, walking uphill. They talk to each other, which of course they have to, because we are talking about moving probability densities around. So we know that communication has to be there. And it turns out that's the way it happens. But there's also the other term here, and that's actually a repelling term. And if you look at it, what it does, if particles come too close to each other, you say, oh, not too close, please, right? You want to keep some distance. We're sort of social beings, if you like. We want to keep some distance. And so this term would collapse the whole ensemble of particles to the mode, and this one will make sure that doesn't happen. So if you look at this, you might say, well, then this term is really important, because it will determine the final uncertainty, right? Now, theory tells us, if everything is smooth, that in the limit of an infinite number of particles, it doesn't matter what I choose for the kernel. As long as it's smooth and symmetric, this will always converge to the right solution. But that's something I do not understand. I can follow the mathematics, right? But I cannot now tell you this is logical, because I do not understand why that is. But in the limit of an infinite number of particles, this formulation will converge to the right posterior. There's a solid mathematical proof for that. Of course, when we have a small number of particles, as we have in the geosciences, high-dimensional systems, then the kernel will become important. But not too sensitive, luckily. Okay. Okay. That's so. To give you an example, we did this on a Lorentz 95 or 96, depending on your preference model. So it's a nonlinear, it's a chaotic system in the parameter setting that we use, and we observe so we have a 1,000-dimensional system. We observe every other variable, and the observation operator. So the connection between the observation and the model states is nonlinear. So we observe x squared. So not x itself and x squared. Now x can be positive and negative. So clearly, when I only observe the squared value, I do not know if the value is positive or negative. So that immediately makes this a highly non-Gaussian problem. But still, we manage to get good results. So all these lines up here are lines when we do not do any data. Sorry, I should say this is time, and this is the root mean square error averaged over the 1,000 variables. And so the difference between the mean of the ensemble, the mean particle, and the truth. We know the underlying truth in this system. No data simulation brings us there, and when we do the data simulation, we are much lower, and the observation, the errors of the observation is about half, We're not about to halve, it's a half in these units. And we observe half the state, so we do get what we want. The thing is, we do not have the exact solution, so because this system is too big, right? We do not have the exact solution. But if we compare this error with the uncertainty in the ensemble, we get the same number of magnitudes, the same order of magnitude. So I didn't show that curve, but they are the same. So the uncertainty that we think we have in the system from the spread of the ensemble is the same as the actual uncertainty, the actual error, I should say. So that's one of the things we can test. And to see how that works, this is just one variable. So I just took one variable in this system, and it is an observed variable. What I have here is the prior. So this is just somewhere in the middle of the data simulation, right? The prior is more or less Gaussian at this moment. And the vertical axis here is pseudo time. So we're going to look at what happens at observation time with particles. And just to show this, I used 100 particles. So I have 100 particles here. And these particles, like I said, they're going to move in pseudo time. And my posterior, remember I measured x squared, is bimodal. Because I don't know if I have a positive value of x or a negative value of x. The observation doesn't tell me. So what happens is that each of these particles, each of these red dots, so again this is only at one variable, so it's just a marginal, what's happening at that specific point in the system, and of course we're doing the whole system at the same time. But each of these particles, so this is the way they move, right? They sort of split here and they move to the two modes as we want them. So this particle flow indeed seems to work. It's doing what you want it to do, and this is one of the ways we can test things, right? We can look at marginals, and then see what happens there. Now this is 1,000 dimensions with 100 particles. Now I think we are, Anyway, I don't want to oversell, but I think we're doing a good job compared to where the field is. Then we push it to an ocean model. This is just a simplified ocean model, just a one-layer ocean model, which in a highly nonlinear regime. I put a lot of wind over the ocean, and the water starts flowing, etc. And the general circulation is a clockwise circulation on the lower half, and an anti-clockwise circulation in the upper half of the domain. And these two currents, they converge on this side, and you get this strongly meandering flow and eddies being formed, etc. So it's a highly turbulent regime. The dimension of the state is about 180,000, and the grid spacing is 10 kilometers. We're talking ocean, so large scale. So this whole thing is about 2,000 kilometers by 3,000 kilometers, something like that. So it's not a real ocean basin, but it has sort of the features there. And what I'm showing here is again the speed of the flow, so the magnitude of the velocity, and it's about 2 meters per second in this example. Observations, we observe the thickness of the layer of the ocean every day and every 100 kilometers. So every 10th grid point we have an observation of the height of the sea surface, of the thickness of the layer, I should say. And we only use 20 particles. So we're really pushing it. We only have 20 states, and we try to reconstruct the whole posterior PDF. Now we have to say something about the kernel. I told you earlier that we use a Gaussian kernel. And so the kernel with sort of a distance between two states is given in this way. We have to define this covariance matrix. We can talk about what we chose there, but this is something that seems to work. For the prior, we actually do need a continuous representation, which is actually an issue. What we do here is probably the simplest thing. We just approximate the sum of delta functions by a sum of Gaussians. So we make it a Gaussian mixture. And if you do that, that's fine, but you need to find the covariance of the mixture, and the covariance of the mixture, we just take the covariance of the ensemble of particles and then divide it by the number of particles. As such that this probability density has the same covariance as the original one with the sum of delta functions. So this is an approximation, and this is the only approximation that we make in this whole system. Something about minimization, well, I don't want to go into the details there. So we apply, effectively, it's in, so the differential equation, we solve it by an approximate Newton method, by quasi-Newton method. Okay, some results. This is the true field at some time during my integration. This is the mean of the particles. I'm just showing one field. I could show 20, but I just show the mean here. And you see they're quite similar. They're not the same, but they're quite similar, suggesting that we're doing something useful. And if we look at the uncertainties, so this is my estimated uncertainty. So this is the variance in the particles. I can just calculate the variance at every grid point from my ensemble. I can compare that to the actual error. So the truth minus the particle mean squared. And then we see that these fields are quite similar. They're not the same, again, but they're quite similar. Again, suggesting that at the first and second moment of this distribution, we got those. Of course, we want to go beyond those first and second moment, but remember, we only have 20 particles, so we can't move it too far. But again, this, like I said, this was pushing it a bit to reduce the number of particles as much as possible. And we can also look at the time evolution of these fields. But in the interest of time, I'd like to move on to the, okay, I don't want to talk about this now. I just want to move on to the conclusions. So, so we have this particle flow method, and it solves the fully nonlinear data simulation problem, which is a small number of particles. And that's the interesting thing, I think. That's new. It's fully nonlinear, but a small number of particles. We have some promising results with ocean hemisphere models. I just showed you something, but of course we have more. If you know what a 3D var is, then this method is equivalent to an ensemble of 3D vars in terms of cost. And actually, we managed to attract the interest of the European Center for Medium Range Weather Forecasting. These guys in Europe, I'm afraid, they produce the best weather forecast in the world still. The US is catching up now, but they're still, and have been for the last 30, 40 years, have been the best in the world. They're interested in implementing this, because actually it turns out that with little changes to their system, we can actually make their linearized system that they have now into a fully nonlinear one. Anyway, that's all I had. Thank you very much for your attention.
Questions?
I want to go all the way back to, I think, your first or second slide.
Okay.
And
you want to see the movie?
no, I don't need to see the movie. This is so outside of my field, but
Yeah.
still, what I don't understand is, if I were attacking a problem like this, I'd start by trying to reduce the dimensionality.
Yeah.
Either do, for example, spatial means with larger cells, and then come up with some sort of, if I know, maybe I'm going to have large cells and just come up with two statistics and then imply something about the distribution within it. Maybe I don't understand, I don't understand why you need that level of spatial resolution.
Well, the thing is that and let's go to this way, we want to do forecasting, right? So we want to do the forecast at as high resolution as possible, right? For global atmospheric weather forecasting is about 10 kilometers nowadays. We want to go smaller. We want to know what the weather is at a 100-meter scale. And the thing is that some of the observational networks are getting us there. We do have observation at 100-meter scale from satellites. Not the whole atmospheric state, of course, but so the observations are there. And we have, of course, a lot of local observation that we want to use completely. And as soon as we do the spatial averaging, then we have to think about, okay, I have a thermometer on top of this building. And now I have my model grid, let's say 100 kilometer by 100 kilometer. how do these two relate to each other? So the model has an average temperature of 100 by 100 kilometer, and I compare that to a more or less point measurement on the top of this building. But this is already an issue, of course, with the resolution that we run now. But if we start averaging, it becomes even more an issue. And so to fully exploit the observations, we just need to try to do this at a high resolution. But I must say that, of course, if we reduce order model, I mean, there are all kinds of people try to use that, or use different grids. So a high resolution grid when you have a lot of observations, a low resolution grid where you have less observation. That's not happening so much in the atmosphere because it's a global system. But for the ocean and also for hydrology, I know people are doing these things. Yeah.
If you mean by that dimensionality reduction, I mean one of the challenges that we face is the observations are not available all over the grids of the model. So when, for example, if you think to just reduce the dimension by a PC analysis, it's challenging because the data is kind of disparate. We cannot just project everything that we have in a lower dimensional coordinate, assimilate, and then recover it back, because some of the data are not available on some coordinates.
Yeah. And perhaps another problem is that if the dimension of the system that we're looking at is more than, let's say, 10, if it's more than 10, then the standard nonlinear data simulation method, which would be a particle filter or Metropolis Hastings or stuff like that, is not going to work. It's too expensive. Yeah, we have to do smart machinery to do that. And as soon as we solve the problem for, let's say, 100 or 1,000, we might as well do 10 billion. He said. Okay.
Yeah. So I was wondering.
Wait, you need a mic, otherwise you're not recorded.
Yeah. So I was wondering, how was it able to tackle the filter degeneracy problem? Like you showed, like 20 particles were able to like 180,000.
Yeah. So the thing is that we. I cannot change that, I'm afraid. Sorry. So the thing is that that in the particle filter, you would indeed, if you go here, in the particle filter, you would try to go from here to there in one step. And actually, the way you do it, you're not moving the particles, you're just giving them, you just weight them to how close they are to the observations. Or you move them a little bit with a proposal density. But the thing is, you try to do it in one step. And as soon as you try to do it in one step, then you have these weights coming in. And with this method, I never talked about weights because I don't need to talk about weights. Because the only thing I'm doing is I'm just smoothly transforming these particles to samples from the posterior. And they're equally likely here and they're equally likely here. And so they all have the same, well, they all represent the same probability mass at all times. I don't need to touch that. It's, sorry, I must say there are people trying to do optimal transportation mapping, do this in one go, but these methods struggle with high dimension still. So, yeah, there's always. Yeah.
When you were formulating the problem for your flow F and Q, you yourself mentioned that there are many different solutions.
Yeah.
And of course, you were guided in selecting a particular solution by the outcome that you wanted to have.
Yeah, yeah.
So that seems to be open to some other possibilities. And are there any, or are they difficult to get? Or?
Well, so that's a. I don't know which way I have to go now. What is this is yeah. So we know we started the prior, and we know we have to end up in the posterior. So these points are given, because we want to have samples from the posterior. That's what we want. But how to get there? So you can formulate this as an optimal transportation problem. So the way we do it, it's not optimal, but it's optimal in that we say, well, we want to reduce the Kubrick-Leibniz distance as fast as possible. But indeed, you can do other criteria. If you use a different distant measure, like Henninger, for instance, I did that, right? I looked at, anyway, it doesn't matter. I looked at different ways to do it. You get sort of similar problems, similar expressions. It doesn't matter too much. It looks, yeah. What else can I say? But okay, and there's and there's sort of two methods, right? You can again you can try to how do I say that? Okay. Yeah, I don't know if you realize that, but there are sort of let's make sure we don't go too much. And so this is one method where we say, okay, we just linearly raise the likelihood to a power linear in the time, pseudo time. Now, and that gives you, well, certain formulations, etc. And then it sort of stops because we don't know how to make a practical algorithm. Of course, you don't have to do this linear. You can do quadratic, or you can do whatever you like, right? There's all kinds of possibilities. So at the moment, this looks like a research field with an infinite number of possibilities. You can go all the way. And you can indeed also look at the optimal transportation. There's huge literature on optimal transportation. And typically those methods are not directly applicable to high-dimensional systems. At least I haven't seen anything that is directly applicable. But yeah, there are too many. So if you give me 10 PhD students, I can easily all send them off in a different direction, literally. Yeah.
So you commented toward the end about the computational savings that you can achieve using this method. Mm-hmm. Can you just talk a little bit more specifically about where that comes from? Is it in the minimum distance assumption or the kernel or the?
So, okay, let me bring up that slide where I say something about that. I don't know where I say it. Okay, anyway, so no, let's do it this way. Give you this. Sorry for the moving around. This will do. Look at this equation. So this is what we have to do, right? Now, any minimization method that I know of in the Bayesian inference works with this gradient of the log of the posterior. So you have to have a method that does that. And that method, that typical method, if you use a Newton method or so, in our field, meteorology, that's called 3D VAR. And so we have to do that, and you have to do that for every particle at the same time. So I have 100 particles, I do 100 minimizations. Now, these minimizations you cannot make parallel, right? Because they are iterative methods. But of course, doing 100 of them can in principle be done completely parallel. However, they need to talk to each other, to this kernel. So each particle needs to know the gradient of the other particles. So suddenly, I had this nice parallel idea, but there is a lot of communication. Every time I need to, and I looked at that, you need the order of n full state vectors need to be sent from one process to the other. So let's say 100 billion dimensional vector has to be pushed around, and then if I have 20 particles, 20 of those have to be pushed around. So the standard minimization, on top of that we have the extra communication. And we have to calculate the kernels, but yeah, that turns out to be, well, not most expensive. Yeah. Does that give you an idea? Yeah.
Thanks. A small question. So, when you distribute, you said in the example of the ocean that you have 20 particles. So in some cases, assume that you may have point observation, or you may have drifters, for instance, in the ocean, and their distribution in space may not be optimal.
No.
Right. So what is the effect of the non-optimal distribution in space of your
yeah? So
observation set?
So let's bring that up. So indeed. So for instance, if you have drifters, then they'll They quickly move away from the hyperbolic points, and they're all going to sit inside the eddy. And that's what they'll do. And I know the flow there. It's quite boring. I don't care about what happened there, right? I want to know what happens at this point and this point, where things. So this, of course, this is an issue. The machinery will still work, and it just means that sometimes I have an accurate solution here, a quite accurate solution here, and other times it will be more accurate here and less accurate there. And so that's in the end the way to look at it. So the uncertainty in your solution will depend on where your observations are. Absolutely, yeah. And in the ocean in general, we don't have many observations. Of course, we have satellites, so we see a lot about the surface, but we don't know what's happening in the deep ocean. And the only way to know this, go there with a ship, throw something overboard, or indeed have some drifters. That's, yeah. But that is, yeah, the sparsity and the irregularity in space and time of the observations is it just means that we cannot get as accurate as we would like to get. But the method in principle can handle that. Yeah, and we're doing that.
I was thinking that a method was popular about 10, 15 years ago in turbulence was the smooth particle hydrodynamics.
Mm-hmm.
And it was based on letting particles sample the flow all numerically. But then at some point they realized that they had to restructure everything on a regular grid and redistribute the particle again, because otherwise you
exactly you would get So of course the optimal way. So I didn't talk about that, but the optimal way to, if you have a drifter, a real ocean drifter, so a buoy or a float, whatever, Argo float, if you want to simulate that optimally, then it has been shown again and again. The best way is to have the equivalent of that observation, which means a drifter in the ocean at that position. So then you can optimally simulate the path of the drifter, and that gives you definitely the best ocean state. But like you say, right, if we do that, then we need to populate this whole numerical model with drifters everywhere at all depths. That will become way too expensive. And so sometimes when we know we have a drifter observation, then locally we can just put a bunch of drifters in that neighborhood and then see how those drifters behave and then simulate it in that way. And of course the drifter positions, the numerical drifters, if you like, they are of course connected to the Eulerian variables that they have elsewhere through the prior. So that information from the observation, from the Lagrangian observation, will be spread out in the whole model. But but it is problematic. They're perfect. They're very good data. Very lot of information, but difficult. Yeah.
All right. So let's thank him again. Appreciate it for coming to the talk. Thank you so much.